Hello. Sorry about, we're talking about improving graphic quality for PDF and strategies for using SVG. My name is Aryeh. I work for Suite Solutions. Just a brief introduction. We're a consulting group. We provide consulting in all parts of the content lifecycle, from the beginning planning stages through information development, delivery, and conversion, whatever part of the lifecycle process you'd be interested in. Some of our clients and partners are listed on this slide. For any further questions, please be in contact with Alan Comment, who I believe has been sending out emails about the webinars. For any technical questions, you can be in contact with me. My email address will be given at the end of the presentation, and if you have any questions, please feel free to ask in the middle or use the GoToMeeting interface to ask questions. The questions that I wanted to talk about during the course of this webinar are: what do we mean by graphic quality, and how do we keep graphic quality high? The nature of this webinar ends up talking a lot about nitty-gritty details about images, but in a way it might be easier to start from the end. The executive summary of what conclusions we're going to come to through the course of the webinar are that we advise people to try to avoid needing to scale images, and because scaling images often is one of the sources of image quality problems, except for SVGs, which you can scale freely. And then we have a couple of suggestions of different types of file formats for different types of images. We suggest SVGs for line art, JPEGs for photographs, and PNGs for screenshots. And the final piece of the executive summary is that we don't advise trying to translate SVGs as if they are regular XML files. We're going to go in a much more orderly sequence through the course of the webinar, but I just sort of wanted to put that up at the front because we may be getting into particular technical details, but all of the details that we're going to get into are basically going to be driving these couple of recommendations. There are hopefully a number of other valuable takeaways through the course of the presentation, but I think that it will be good to sort of keep in mind that when we're talking about details of image formats and so on and so forth, the reason that we're talking about those is we're trying to come to decisions about what to do practically with your images when you're trying to publish and produce output. So these are some of the takeaways, I think some of the most useful takeaways that we're going to come to, but hopefully there will be others as well. And again, if there are particular questions that I don't cover, so feel free to ask. Okay, so just to start from the beginning, we're going to talk about what we mean by graphic quality. I'm clearly, we know it when we see it. If you see a good quality graphics, you can immediately say, well, this is much better than bad graphics that sometimes you've seen in various publications. But there are many different types of things that make one graphic better than others. So we're certainly not talking today about just having clear graphics in the sense of information design. That's a whole new separate topic, making graphs easy to read, making tables easy to read, making them useful to the reader. That's an important part of giving clear graphical information. But right now we're basically talking about things that are to be more specifically talked about and described as image quality. I just have a couple of examples, all taken from a single image. We run into different kinds of ways that images get degraded when we try to use them. One way that they get degraded is they become less sharp. Another way is we could not have enough detail. You know, this example I have it pixelated. There are other ways that losing detail can hurt you. This is just one way where the details have been lost. And then another sort of axis of quality is trying to get the colors to come out the way they should. So we're going to talk a little bit about the different things that one might naturally do during their workflow that could affect these kinds of image. They can cause these kinds of problems for images. So we're going to talk now a little bit about the nitty-gritty. What's the difference between the different kinds of image formats that are available to us? We have choices when we have an image that we're going to be using in our data publications, or basically anywhere. If you're using it in FrameMaker or in InDesign, it doesn't really matter. You do it when you're producing images that you're later going to be using. You have a couple of choices of different types of file formats, and it's useful to understand what the difference is between the different choices. So all images are basically broken down into two broad types. One type of images are bitmaps. These are images that are made out of many separate dots, and if you would blow them up with a magnifying glass, you could see the dots. Also, if you scale images, you can see the dots. It's not always the case that the images will show the dots like in this example, but when that doesn't happen, that's because the image has been artificially smoothed. The dots are really there. It's not that we've managed to get additional quality. It's as if you blow it up with the dots and then you run some sort of filter on it to try to clean things up. So bitmaps are made of dots, and there's nothing you can do about that. They're always going to be made out of dots. If you scale them up, they still have dots. There are various things you can do to try to, if you're adjusting sizes of images, that will hide that fact, but at the end of the day, bitmaps are going to be made out of these separate dots, these individual pixels. So all photographs and screenshots will be bitmaps. I'm not 100% sure, given that this is going over the webinar, that the webinar is going over the internet, and I'm not 100% sure if you're seeing exactly the same thing I'm seeing on my screen. But we will be sending out the slides afterwards, so if two things both look blurry, so then hopefully when you actually see the slides later, you'll be able to determine what it was that I was talking about. So those are bitmaps. Photographs and screenshots are always bitmaps because the way we acquire an image for a photograph, the way a camera will pull in a photograph, and the way your screenshot tool will pull in a screenshot, it will do that by reading dots. So the natural format for photographs and screenshots are bitmaps. There are also a different category of vector images. Vector images are things that are made out of lines, curves, other shapes, so that if you stretch them, they retain their quality, because if you precisely define a curve, then it doesn't really matter what size it is. The shape is the same. If you draw a square and then you stretch the square to be 5 times the size, it's still a square. It doesn't start getting blocky or otherwise degraded. So vector images don't degrade, bitmaps do degrade, but on the other hand, there are a lot of images that we don't have a choice. They're naturally bitmaps. So vector images are generally better. They give us more flexibility. But for a lot of cases, we just don't have a choice. Screenshots and photographs are going to naturally be bitmaps. So once you know that broad category, we have a couple of different kinds, many different kinds of file formats, truth to be told, that you can use within these two categories. I'm not going to talk about, there are hundreds of different file formats that one could theoretically use. Practically speaking, most people use only a small handful of choices. And we're just going to discuss that short list. So if you're talking about bitmap formats, there are probably the four that I have listed here are the most popular or familiar to most people. The GIFs, the Windows bitmaps, BMP files, and PNG files are all basically similar. They store bitmap images. They are all lossless, which is sort of counterintuitive. You wouldn't necessarily think that images throw away data, but we'll see in a moment that not all bitmap formats are lossless. So they're basically, you have an image. These files are all ways, in theory, equivalent ways of saving those images. If you would save something as a GIF file and then you could convert it to a PNG file, and it would be the same, in theory, as if you saved it directly as a PNG file, because it's the exact same information. They're just different formats. But it's not so simple, of course. PNG is a newer format, and it supports additional features. In particular, it supports alpha channels, which is a way of making parts of an image transparent to different degrees. In technical documentation, that's not necessarily such a useful feature, but for a lot of practical uses, PNGs are therefore preferable. Another more important difference is that it supports many more colors than GIF. GIF is, if you save an image that is in bright colors, that is supporting a 24-bit color, let's say, 24 bits is a way of describing how much information each pixel, each dot has to represent its color. So GIF can't represent that. So it will have to throw away color information. So if you're starting with an image that has many colors, GIF can't necessarily save that. So PNG is certainly preferable on that front, and that does affect documentation. BMP has similar to PNG. It does support more colors, but PNG usually has smaller file sizes, and PNG is more widely supported on the web. So PNG is a format that you can use in most different contexts. You can use it directly on the web. You can use it in documentation that is going to print. It's generally the easy choice for images that need to be lossless, and we'll describe in a moment what that's a trade-off against. There's another image file format which I think many people will also be familiar with, called TIFF. TIFF is actually, although in theory it looks like it's one kind of file, it's a standard that has many different options in it. So it could be you can have a TIFF file produced by one correctly functioning program that can't be read by another correctly functioning program that supports TIFFs, because there are many different possible subsets of TIFF that can be supported. But the main downside for using TIFF, so there is a common group of features that most tools do support, and it supports overlapping features with PNGs. So for most of the reasons you'd want to use a PNG, you could just as easily use a TIFF. But web browsers do not display TIFFs. So that alone generally tilts the balance in favor of PNG. So describing bitmap formats, we've discussed 4 different bitmap formats. They all have overlapping purposes. There are many others as well, but practically speaking, these days, most of our bitmaps, among these 4 choices, we would probably tend to use PNGs. That being said, there is another very popular bitmap format, called JPEG. JPEGs are not lossless. They actually remove data. If you take a photograph and then you save it as a JPEG, you're not actually retaining all of the information that your camera captured. JPEGs are designed to produce smaller files than the other formats that we discussed before, because the only thing that JPEG is trying to do is it's trying to make things look the same rather than actually be the same as the source image. So it takes advantage of the natural way that people view images to try to remove detail that you won't notice. There are quality settings when saving JPEGs, and that the choice of a quality setting can affect. If you pick a higher quality setting, it'll have less loss, and it'll also produce bigger files. But but JPEG is always going to be lossless. Unlike, I should make a caveat that a lot of these things have obscure forms as well. There are certain forms of JPEG that are not commonly used that actually are lossless, similar to PNGs. But in the normal case, JPEGs are going to throw away some data, and they are good actually at doing this, generally speaking, but they work really best for photographs. The photograph, you can, you're looking at something which is a natural thing for the eye to see, and this algorithm that is used to try to compress JPEGs to make them smaller and to try to retain as much of the normal appearance is tuned to work well for photographs. So generally speaking, if you save a photograph as a JPEG, it'll look great. You'll get smaller file sizes. There's really no downside as long as you have reasonable quality settings. But when it comes to things like screenshots, so then the algorithm doesn't work so well. I don't know if this is coming through on GoToMeeting, but I have two samples here. On the left, I have a screenshot without the JPEG compression, and on the right, I have one with the JPEG compression artifacts. That's I don't know if it's coming through, but hopefully you're able to see that there's a subtle blurring around the words, and that blurring is typical of what happens when you save screenshots or text or line art as JPEGs. So generally speaking, JPEG is a good choice for photographs, and PNGs are a good choice for screenshots and line art that is bitmapped. So if you have something that's already a bitmap, it's already made out of the dots, you don't have a choice of going to vector format, then you probably want PNGs for those kinds of things, and for photographs you want JPEGs. These two slides basically are the justification of the recommendations that I made at the beginning in the summary of what our conclusions will be, that JPEGs for photos, PNGs for other bitmaps such as screenshots. Okay, so that is a brief summary of bitmap graphics. When it comes to vector formats, so there are, again, many different possible formats, but there seem to be two that are most popular, for our purposes at least, EPS and SVG. EPS is based on PostScript. It's an older, more established format. SVG is the newer version on the block. Before getting into specific details about these formats, I wanted to point out that EPS and SVG files don't necessarily only have vector images in them, because you can stick some of these other bitmap images directly inside them. Just as an example, if you have a photograph and you insert it into an EPS or an SVG file, and then you mark it up with callouts, well, the callouts will be vector graphics. They're made out of those lines and curves and so on and so forth, and they will produce clear output at whatever size you want to produce. But the photo is still, despite the file format, the photo is still the same bitmap it always was. There's nothing that can be done about that because the source that we have is made out of a bitmap. Okay, so those are basically our two choices. EPS and SVG are basically our two choices for vector formats. In the world of data specifically, there are a couple of considerations that advantages for SVG. So in most areas, I think these days SVG happens to be advantageous for the simple reason that web browsers can view them directly. There is a small list of image types that web browsers can view, and SVG is one of them, with the single exception of Internet Explorer. Internet Explorer, which of course is still a huge part of the web browser market, does not yet support SVG. Microsoft has announced that they will finally support SVG in version 9, which is the upcoming version. So that's pretty exciting for just to be able to get vector graphics onto the web so that we don't have to worry about any particular extra processing steps. That's still in the future. It's the first chance to be able to use Internet Explorer is still some time away, and even once Internet Explorer 9 is delivered, there's still going to be a lot of users who will remain on older versions. So it may take a while before it becomes useful for everyone. But it is an advantage just simply because a lot of graphics do have a long life cycle. So if you create an image as an SVG now, and at the moment you might have to have special handling, sometime down the road you'll discover that all of your users will be able to view SVGs directly in their web browsers. Okay, specific to the data publishing pipeline, both Antenna House and XCP have some problems with supporting EPS files. There's a real big downside, which is that if you don't know that they don't really support EPS files, you might think that they do and get a particularly bad output. And the reason for that is both of XCP and Antenna House out of the box, when you include an EPS graphic, they will produce output showing your graphic. But the way they both do it is that EPS files have a little, like, almost thumbnail. They have a tiny bitmap image inside them intended just as a preview of the real image. Not all EPS files have it, most of them do. And in those cases, both XCP and Antenna House will use that thumbnail preview image instead of the real image. So if you use an EPS graphic, you'll get output, but it'll be degraded, and I don't even think that it gives good error messages to explain why, because it's only using this thumbnail that's stuck inside the EPS file that's really intended only to be. Antenna House does support EPS files, particularly useful if you do have legacy EPS graphics. But the way it does it is it needs to use some external tool, either GhostScript, which is a PostScript processor, which is free, or Adobe Distiller, which is not free. And using either one of those, it can actually produce EPS graphics and insert them into PDFs the way they are meant to be viewed, but it is slow because it has to run those tools for every graphic separately. So publication that uses this is slower than it would be with SVG. So this slide basically explains our recommendation for using SVG over EPS, at least in the Ditto world. Okay, so now that we've just basically talked about what our broad choices are, I want to talk about some of the specific different things that happen to images. We're mostly going to focus at the moment on bitmap images. Some of these issues will also be true of vector images, but not as much. So the first thing we're going to talk about is image resolution. So image resolution is, your images are made of many dots. They're called pixels. Each dot is a pixel. So if the size of the image is going to be defined by the number of the way I wrote it in the slide is correct, but I think it may not be completely clear. If you need to figure out, when you have a certain number of dots, you still need to figure out how big the image should appear when you're actually viewing it on the screen or in print. So the idea is the more dots you have in a given amount of space, the clearer your image is going to appear, because you have more precision. If you have more pixels in a given amount of space, you're going to have a better looking image generally. So the size of the image, the way you actually see it, is going to be basically the number of pixels you have in your image divided by the number of pixels per inch. The reason why it's important to think about it this way is because this is a frequent measurement that you'll actually see in different tools when trying to work on images. Sometimes it appears as dots per inch and sometimes as pixels per inch. Those terms are both used interchangeably. So DPI or PPI are measures of telling you how many pixels are supposed to appear in a given amount of space. Sometimes images use metric measurements as well, but I think the abbreviations DPI and PPI are still more popular for whatever reason. So just a specific example, most screens are around 96 dots per inch. Some people have higher numbers of pixels per inch. It's not so frequent anymore to have lower numbers. So if you have a screen that's 96 DPI and you have a screenshot that is 960 pixels wide and you don't scale it, you just put 1 pixel of the image to 1 pixel on the screen, then it'll appear to be about 10 inches wide on the screen. If you have 96 dots every inch, so then if you have 960 of them, then you get about 10 inches wide on the screen. So if you have a particular DPI that you're using, then you also know how big the image will appear when you're actually viewing it. So screens are usually about 96 DPI. Print usually only looks good when you have somewhere upwards of 225 DPI. And this is a bit of a contradiction, because if you have an image that you just want to be 4 inches wide, supposing you have a choice about how many pixels this image is going to be, let's say you're taking it with the camera and you need to adjust the camera settings to take a certain size image. So if you know it's going to be 4 inches wide, well, you're going to have to pick a particular real number of pixels to put in your image. You're going to have to take your photograph somehow. And so the screen and the print are going to be at odds with each other. screens are going to have much lower DPI than print. A lot of printers are advertised as, even your home printers probably advertise as printing 2400 DPI or something. But when it comes to a printer, the dots per inch really are dots, not necessarily pixels. The printer will actually, if you have a single pixel, a single dot of your image, it will actually have many small dots of ink. And the reason for that is that if it produces many small dots of ink, it can produce approximate colors and shades. If you have a bunch of small black dots instead of one large black dot, then the black against the white paper will give an impression of gray. So even if you don't have any gray ink in your printer, you can use these small dots to give them to produce additional colors and shades, and therefore the high DPI doesn't necessarily represent how good an image your printer is capable of producing. That's why the 225 DPI number is so much lower than what in theory a printer can do. In practice, if it could really produce 2400 pixels per inch, you would never need that. And the reason for that is that the limit of human vision, it depends how close things are to your eye really, but at a normal distance of a foot and change or something, people seem to be able to see around 300 dots per inch. So if you're going to have a number of real pixels that is way higher than that, you have more information than you need. Your viewer isn't really going to be able to see it unless you really expect your viewer to be looking at your images with magnifying glass. Okay, so resolution basically is the question of how many dots, how much visual information we have in our image for a given space. Okay, so there are two takeaways here. One is that if you're producing an image for a screen, you should be aware of this 96 DPI goal. And if you're going for print, you should make sure that you have a high enough DPI, somewhere over 225 DPI. Okay, so I had this example before, given an image with low resolution, and I just wanted to elaborate on what's important about the fact that the image has low resolution. It's important to realize that there's nothing I can do to fix an image that has low resolution. If I took a photograph and I don't have enough pixels, I can hide the blockiness with Photoshop, I can smooth the image, I can use the sharpen tool to perhaps get the outlines to be more precise. But I don't have the visual information there to have a real, original, clear image. So I might be able to patch things up a little bit, but I can't retrieve the missing pixels. So it's when we're trying to figure out what resolution to save our images as, we need to be aware of what our goal is. We can't sort of patch things up on the fly afterwards. If you have higher resolution than needed, you have at least better chances. We'll talk about in a moment why it's not ideal to have more than you need also. But if you have too few pixels, you're stuck. You can produce an image that doesn't look completely terrible, but you can't produce anything that really looks great. With photographs in particular, an image that looks fine on the screen may not have enough resolution to look good in print. This is an important thing to know if you're working on your computer screen and then you're just hoping that everything that looks fine on your screen will look fine the moment you print it without trying it. And the reason for that is that the printer, as we said, is capable of much higher resolution. The printer is capable of printing many more dots, and so the resolution that you're comfortable with on the screen, that looks fine on the screen, will just simply look all blocky and missing detail when it goes to print. So it's important to be aware that because there's this distinction between screen and print, that people might take an image from some source on the web and it really won't work out in a book. Okay, so so far we said that it's important to have high enough resolution. You need to have enough dots. What about if you have resolution that's too high and you want to scale your images down? So I started to try to illustrate this particular point that I'm about to make, but I unfortunately the graphics that I started to make I did not think were actually enlightening. So I hope you'll bear with me while I try to explain what what's going on in this slide. So if I wanted to show, I have an image that is 960 pixels wide, let's say. And I'm showing it on the screen, so then it would naturally be about 10 inches wide. So let's say I really only want to show it at 5 inches. I want it to be half the size. So even though we all are familiar with using software, we just stretch it, but it's important to realize behind the scenes, what does the software have to do? The software necessarily has to throw away half the pixels because it's only going to have half the pixels. It's not able to just, the screen has a natural number of pixels, and it can't be made any more precise. We can't just simply shrink that image and then make it more precise in that section of the screen, because the screen only naturally in that space has the 480 pixels that exist. So if we want to show a 960 pixel image in 480 pixels, we have to throw away half the pixels. So realizing that that's what our software is going to do to us, no matter what tool we're using, whether we're using Word or we're using FrameMaker or we're using InDesign or we're using a tool chain, they all have the same problem. If we're going to shrink it, we have to throw away half the pixels. Now, the problem is, I'm just trying to illustrate some of the problems that will happen. There can't possibly be a perfect solution. Let's say I would just try to solve the problem by erasing every other column. If you imagine that there's 960 columns that form this image, and I only want it to be half as wide, so let's say I erase every other column. Now I have an image that is half as wide. It has half as many pixels. So this will work for certain things, but if you imagine that the image that I started with was a screenshot, and on my screen I have a line that is exactly 1 pixel wide, and it appears in one of the columns that I erased. So I will now have erased that entire line. So the image that I've created that's smaller now looks completely different, because I used to have lines in it, and now these lines are gone. So this is a simplistic solution about how you can shrink the image, but it's worth being aware that whatever solution we come up with, it's going to face the same sort of challenge, that certain cases, when I shrink the image and throw away information, I'm naturally going to end up with an image that actually looks different. The idea then is to try to pick a way to do it, to shrink the image, where the smaller image is likely to look pretty similar. So just a slightly more fancier example of what you can do. You can take each pair of pixels. Let's say I'm going across the image, and now instead of throwing out every other pixel, I've got a more sophisticated solution. I'll take every 2 pixels, and if one is white and the next is black, I'll pick a gray right in between. I'll make each color the average of each pair. So now, again, I've shrunk the image to half the size. And by doing so, though, now I've got more data. If I had that 1 pixel wide line, I can't possibly have erased it anymore. Now that information is still sort of there, but it's worth realizing that I still have degraded things, because if I had a black line that was 1 pixel wide, and now I've shrunk everything and I've averaged it with the white line next to it, the white space next to it, now that formerly black line is gray, because it's halfway between white and black. So I'll be able to get the gist of the image, but it's still not the same as it was originally. So even this more sophisticated solution is going to still lose some of the image quality, even though we started with more resolution than we needed. Sounds like if you have more resolution, you should be doing great, but it's not always the case. In practice, scaling is usually more sophisticated. It's something like this averaging solution, but with a more sophisticated way of doing the averaging. It uses a series of related pixels, and it gives them different weights, and therefore it tries to give as good an image as can be expected. But you can still find images where scaling to particular values produces much lower quality images, even though you started off with much more resolution than you really needed. There happens to be an exception, which is, again, it's worth mentioning just because it kind of comes up here, but it's a little bit off of the main flow of our general webinar right now. But that more sophisticated way of shrinking images is used by almost everything except for Internet Explorer, but Internet Explorer can use it too. It just needs this one line that appears in the slide added somewhere to the CSS file that goes with the HTML that's displaying your image. Basically, if you add that line, then it'll use the same fancier scaling method that we've been talking about. So we've given some extreme examples where you have this 1 pixel wide black line, and practically speaking, most images are not going to suffer as much as that from being resized, but they all will degrade somewhat. Photographs will usually do okay, because to start with, you're not going to have any 1 pixel wide black lines, or it's going to start with an image that isn't based in pixels anyway, so the appearance will tend to be retained in a much more visually satisfying way, but screenshots won't do as well, because practically speaking, screens are low resolution. If you're taking an image of a screen that you're showing on a computer screen, a lot of the times the designers will take advantage of features that are exactly 1 pixel in size. They've drawn particular lines or buttons or icons or what have you. And if you're now going to show a resized version of the same thing on the screen, so you're going to run into these kinds of problems that we've been describing. So the only real solution, the ideal solution, is that when you originally create your images, it's best to produce them at the exact number of pixels that you'll really need. Now, there are a number of second best choices, but it's worth being aware that that's generally going to produce the highest quality output. If you have an image that has much higher resolution than needed, then when you scale it down, it'll also be fine, but you'll end up with very large files. So it's an option, but generally, if you can get away with it, particularly with screenshots, it's really best if you can get away with taking taking your screenshots at the exact resolution that you're going to want to display, at least for the screen. One of the other consequences of this is that, naturally speaking, screenshots will tend to look so-so in print, because you're taking what is effectively, from the perspective of print, you're always going to be taking a low-resolution image. So unless it's an example where you're willing to throw, to shrink, print it at a much smaller size so that you effectively have more data per inch, then it's going to have to look somewhat more blocky, just naturally speaking, because it really is. A lot of us are so accustomed to staring at the computer screen all day that we're not really thinking about our screens being blocky, but they are. But if you do compare text on your screen to text in a printed book, you'll easily be able to see that the screen has fewer pixels. It's definitely blockier, and therefore printing screenshots is just simply a tough problem. If you somehow or another have something that could be displayed at different sizes, and you can take a screenshot that is way bigger than most people tend to use it, then it might really look good in print. So if that's an option with a particular tool that you're using, you have some sort of interface that actually scales, and then you have a way of taking a screenshot that is much larger, then you can produce screenshots for print that will really look high quality. Okay. Let's talk a little bit about color. Color now does apply to vector images as well. Just a little bit of background about color itself. I used to think that all the colors of the rainbow meant all of the colors that exist. It's not true. There's no brown in the rainbow. And color is actually something that's fairly difficult to describe, and therefore difficult to capture for a computer. The human eye is doing something quite complicated. When you see different colors, the eye captures 3 different ranges of color, with the occasional rare person, very rare person, 4 different ranges of color, but almost everybody captures 3 different ranges of color. But then the brain actually does a lot of processing on that. If you are sitting in a room with a yellow incandescent light, you'll see a piece of paper that looks white, and if you go outside into the sun where light is much more blue, the paper still looks white. And the reason for that is that the brain actually tries to correct colors. It figures out what colors things should be based on the other colors that your eyes are seeing in the other parts of the room, in the image, in the area. So one thing that is going on is that the eye is actually capturing a lot of different information, and the other thing is that the brain is interpreting those colors in context. So that makes color something very complicated and something that's hard to capture in a reliable and complete way. So it's a little bit useful to have that background information to realize that colors can, some of the ways colors can go wrong. Colors, when you display them on a I'll go in the order of the slide. The colors are different devices are physically capable of showing different ranges of color. The colors a device can show is its color gamut. Your computer screen can't actually show all the colors of the rainbow either. Not even all the colors of the rainbow, let alone all the colors that exist. computer screen is going to be limited by the device that you're actually looking at. Different screens will actually be able to show different colors. They can't all show the same color. Different monitor settings will show you different colors when you're looking at what is in theory the same image. And printers can show yet a different range of colors. And those colors aren't necessarily the same as the range of colors that you can see out in the world at large, because your eyes can process a different range of colors. So screens and cameras all tend to use one way of storing color information. When we're trying to figure out what is a color, this is brown, this is red, this is green, this is indigo. So in theory, if you really wanted to be precise, you would have to store a whole huge amount of data for every dot. You'd have to figure out the whole spectrum of all of the different colors that in theory could exist, all the different wavelengths of light, and their intensity at every different wavelength. And that's completely impractical for most of our purposes and completely unnecessary for most of our purposes. The simplification that we generally use for screens and cameras is that screens and cameras do things by trying to measure intensity of red, green, and blue, or to display different intensities of red, green, and blue light. And by producing red, green, and blue light on your screen and mixing them, you have a bright red and a bright blue, you'll see a purple. So using the fact that your eye is basically looking for red, green, and blue, we're taking advantage of this feature of how people view things to simplify our way of displaying color. So screens and cameras are going to use RGB color. And sort of almost aside of, it's almost a separate point, not necessarily related specifically to the choice of using RGB, but screens and cameras support a wider color gamut than printers. That means that they can show more distinct colors than printers can. More distinct colors is not a good way of saying it. They can show a wider range of the different possible colors that the eye can see. Printers, on the other hand, use a completely different way of trying to simplify the process. Instead of having a different ink for every possible color that you could possibly see, printers generally have 4 different colors. They can have more. Printers generally use cyan, magenta, yellow, and black inks, CMYK. The K is black. Sometimes they have a number of others. Sometimes you can have printers that specifically have one specific spot color, meaning that you know that you're going to have to produce your particular corporate shade of blue. You can actually have a printer with some of that particular shade of blue in it. And instead of trying to estimate the color by mixing the different colors the printer already has, you can actually use spot color to add a new color. But both screens and cameras and printers are going to do the same thing. They have a couple of colors available to them. They are going to mix the different colors so that we see as many different colors as possible. So it's important to realize when going to print that when we're going to be changing from one representation to the other, we're going from this red, green, blue representation, which is basically the format that most of our images are going to start off in. If you start off with a screenshot, it's going to start off as RGB. If you start off with a camera, or any normal camera, you're going to start off with an RGB image. And when you actually go to print, somehow those RGB choices are going to have to be converted to intensities of CMYK. And given that printers can't show the same color gamut, they can't show the same range of colors, there's going to have to be some conversion that's going to go on that's going to change colors in a way that seems reasonable. So there's a tool to try to make this all work, and that tool is color profiles. Color profiles are basically files that describe the color space that is available to the different devices. So images can start off with a color profile from the camera, and printers can have color profiles that describe what colors the printer can print, and then your software should be able to use these profiles to convert the images to produce output that looks right. But given that we're going to, naturally speaking, you're going to make this conversion when going to print, so the we're stuck in a way. The CMYK printer is not going to be able to represent all of the colors that theoretically I might have in a single picture. So we have algorithms that try to figure out a way to convert these images from one color space to one color space to the other color space, and from one gamut to the other gamut. And the profiles are the tools that most of the software use to try to make sure that it does it appropriately for the particular devices that you are using. So it's important to have tools that actually use the correct color profiles when doing these kinds of conversions. Most of the high-end tools will in fact do this. If you have do some intermediate image processing, sometimes tools can ignore or rip out or remove color profiles. So it's worth being aware that this is a concern. If you discover that your colors aren't coming through the way they're supposed to, it could sometimes be a consequence of not having correct profiles attached. If you look at a lot of the Adobe tools, they'll produce, for instance, they'll produce CMYK separations. That means they'll produce the amount of each color that needs to get produced by the printer to produce good output. You'll often see there are a couple of choices about how it should do the conversion. So I think the typical choice that most people use is perceptual. What that means is it's basically a model of trying to make things look right to the human eye, that we're going to use the colors we have available to us on the printer, and we're going to try to make sure that the image looks similar to our eyes the way it originally would have looked when it first was created. It's not going to be perfect, but that's generally good enough. Again, there are all kinds of details that might make things look stranger, like when you print, then maybe in different lighting it will look more accurate, or in other lighting it will look less accurate. But that's basically the process that we would use. Because of all this complication, the real takeaway from this is it's good to do a test print. When you are going to print something that is going to, if you're going to be printing a book and you need to produce a large number of copies of the book, it's very valuable to do a test print of each of your various types of images and make sure that the colors actually come through the way they should. I worked with a company that published a book with testing that didn't go through well, and they later described the photos in their book as having radioactive colors. That's just sort of one of the risks of not having all of this toolchain worked out the way it should. So the first step is to just try to make sure that you get a test in, and therefore if the whole toolchain isn't connected correctly, then you can start trying to track down what might have gone wrong with your color processing. Generally speaking, on the web, you don't have as much control over how your colors are going to be displayed. You don't necessarily know what kind of monitor people are going to be looking at if they're looking at things on the internet. Different monitors have different color characteristics, so there's less that you can do. And I guess it's really just a side point. It's not typically one of the things that is high up on the list of things that make or break image quality, but it's worth noting that one of the other disadvantages of scaling images are that most programs actually scale images in a way that can change color slightly. The reason that they do this is basically because it tends to be slight. It's rare that anyone cares. So there's just in terms of the raw details, images, it might not be worth going into. Images can have are represented in a non-linear way. Colors, the eye doesn't see colors in a straight line of different color intensities, and therefore images are stored in the colors in images are not stored in that way. But if you're going to scale images, and therefore you need to be able to average different colors, you need to average them in a way that represents the genuine color intensities and not these color intensities that are just the way we perceive things. So the takeaway from that comment that doesn't appear on the slides is basically there's a slight additional reason to avoid scaling images, which is that it can affect their color a little bit. Okay, so I think we mentioned this in passing towards the beginning. One of the big things that people had hoped to get out of SVGs are that SVG files, unlike EPS files, they are just simple XML files. And a lot of us, most of us are doing all of our editing in data. It's also XML, and we have a tool chain to get XML translated, and it doesn't involve changing all the structure of our XML files. It just translates the text. So we already have this full tool chain. We have our images that are in XML. Wouldn't it be great if we could take all of our callouts or all of our labels or all of our text in our images and just simply send it out for translation without actually having our translators need to tinker with the image? So unfortunately, it doesn't work out. And the main reason it doesn't work out is because once you have text inside an image, the text has very specific layout requirements in order to look right. If you have callouts, you can't have your text at arbitrary places. It has to go straight next to the line that attaches to the part that it's labeling, let's say. So if you would want to translate SVG files like regular XML files, so the text would be replaced, but the text wouldn't get reflowed to make everything work out well. One example is that a label in an image will frequently require much more space in, let's say, German rather than Japanese. So if you allot a lot of space for the German, then when you get to the Japanese version, then all the text will be all way out on the side, nowhere near the line that connects the text to the portion of the image that it's labeling. So it's not so simple to simply change the text. Generally speaking, other parts of the graphic need to be tweaked as well in order to make the new language work. And so therefore, we're still sort of stuck, even with SVG files, using a standard image editor to translate SVG images. Because part of the work is just the text, but additionally part of the work is trying to get the layout right. Hopefully down the road somebody will come up with a more sophisticated solution. SVGs in theory could be modified in more sophisticated ways automatically, but I don't think that there's any solution out there that I know of yet that solves this problem. So therefore, we're still stuck with the same old advice that we used to give, which is that SVGs, just like EPS files, any sort of graphics with callouts, if you have some graphic and you have callouts, it's best to use numbers as your labels if you're going to need to translate your graphic. And that way, if you only use numbers, you don't have to translate your graphic. Instead, in the body of the text, you can just say number 1 is the on button, number 2 is the eject button, number 3 is the power cord. And you can therefore translate your text and use the same image for all languages. So it's not ideal, it doesn't produce the same kind of beautiful output, but in terms of workflow, in terms of trying to make sure that things are translated on a cost-effective basis and making sure that things get properly updated and that all languages see the same sort of thing, it's generally advantageous to try to just, unfortunately, just to number your callouts and to deal with creating legend in the text. I mentioned earlier on SVGs on the web. Soon Internet Explorer will start to support SVGs. But for now, the lack of Internet Explorer support means that you need to convert SVGs to PNGs when you're going to produce output that shows up on the web. It's an open question when this will no longer be necessary. Although we're soon going to have support in Internet Explorer, it's worth being aware that, that there are some corporations that require that their users all use Internet Explorer 6 because of applications that exist on the corporate internet that don't work with more recent versions of Internet Explorer. And because that's the case, sometimes Internet Explorer 6 has been out for many years. So the mere fact that a new version of Internet Explorer exists that has the necessary support doesn't tell us when you'll be able to rely on it. And to a large extent, the question of your user base, some companies have users that upgrade much faster than others. Some companies that are on the leading edge of fancy new I don't know, software or whatever, then they'll find that their user base naturally also upgrades as soon as new version is available, and therefore they'll be able to start using SVGs very soon. Others that delivered to corporate markets that might be much slower may have to wait many years. So it's a value to just sort of have an awareness of what your user base is actually using. Generally speaking, there are analytics tools that allow you to get this information. If you're producing things on the web, you can use these analytics tools to figure it out. Often enough, people already are using these analytics tools. Maybe different departments in different companies will already be using these tools, and it's just a question of getting the necessary data from whoever already has it. So this is true of a number of things, but in particular, hopefully in the near future, it'll be a relevant question for SVGs as well. I think that covers everything I wanted to talk about it today. Are there any questions?
I have a question. Can you hear me?
Yes.
So in my use of SVG, I find that when I develop an EPS in Illustrator and then save it as SVG, that flavor of SVG is not acceptable to the open toolkit, and I have to take it into Inkscape and then do a save as, because for some reason that SVG that Illustrator produces doesn't work. So that's the way it's supposed to.
What version of, how are you producing your output? What tool are you using?
The open toolkit 1.4.1 in for PDF FO with an XCP renderer.
With
RenderX.
So yeah, it could be a limitation of XCP, of the particular version of XCP. It's not really a function of the toolkit itself. XCP supports a particular subset of SVG. I would strongly suspect that there's a way to save it directly in a way that XCP would support, but you should probably ask RenderX directly. The toolkit is simply copies over the file. It doesn't actually do any processing on it in that workflow. So it's XCP does advertise that they only support particular features of SVG, and I'm guessing that Illustrator is just using something that it doesn't support. But it could be possible that one of the options in Illustrator might allow you to save it in that subset that RenderX supports, but they may already have that information on their forums. I don't know off the top of my head.
Okay, I'll check it.
Okay. All right. Any other questions? Okay, thank you very much. Have a good day.